afternoon, folks. My name is Ahmed Sanaullah. I am a part of the research team at Red Hat, and presenting with me today is Sahan, who is a PhD student at Boston University. So we heard this morning, specialized hardware is absolutely wonderful. It's great, it's amazing, it allows us to do our workloads with a lot of efficiency. We're able to do stuff, we're able to do more stuff within our power and hardware budgets, or we're able to do the same amount of work but with a smaller budget. The challenge with specialized hardware is that it's difficult to program and use effectively. I mean, if you look at the software development flow, it's so extremely efficient because you have, platform that's agnostic software running on top of a general purpose OS, running on top of general purpose hardware. So there's a lot of reusability, there's a lot of guarantees. Things you're able to sort of focus it on part of the stack and do the research, innovation, or product design over there, and everything else works reasonably well. But if you contrast that with the hardware development flow, specifically specialized hardware, not so simple. I mean, you're looking at way more layers in the stack, and you're having to customize at multiple points just to really leverage that flexibility that the stack offers and to get that performance and power efficiency out of it. But there's a way to resolve that. There's a way to sort of bridge the gap between the development flow of specialized hardware and bring it closer to how streamlined software development flow is, and that's through hardware software co-design. It's really nothing too complicated. It's not like a magic pill. It really just says that hardware traditionally has worked for niche applications, but now there's actually a lot more workloads that will benefit from it. So we should look to design hardware with the interfaces and abstractions that allow software to leverage it. And software typically has been designed for not only general purpose stacks, but now we should be looking to develop software with the assumption that perhaps at some point we will need to leverage non-traditional hardware in order to get that efficiency for our workloads. And so CoDesign stands for CoDesign. Great name. For a lot of effort. Anyway, so the CoDesign lab is located on the 12th floor of the CES building. It's an on-premise research lab which advances specialized hardware projects, with CoDesign being sort of this core part of that, core focal point to that research. What it isn't is a replacement for the shared infrastructure that we have. Because it is more like an on-premise incubation step, because the current infrastructure that we have, the support for them is really not there. When I talk about support, I'm talking about very low-level system support, like network controllers and PCI controllers and memory controllers. But we need that support to do the research, and we need to do the research to, bring the support up to par. And so that's where CoDesign comes in, is that on-premise incubation step that allows us to start the projects, get them to a state of readiness and completeness, stability, and then transition them into the larger infrastructures, whether it's at the cloud or the edge, and then continue that research as needed. And so, there's a lot of benefits to doing this stuff on premise. We have more control over the hardware, because we're not looking at just FPGAs, it's FPGAs, DPUs, microcontrollers, all that wonderful stuff. More control of the software. It allows us to try out these non-typical, deployment configurations, and this collaboration. And the most important part is, again, this is not supposed to be a replacement for the existing large infrastructure, but rather sort of that step towards deploying stuff over there. So there's one research project going on that actually exemplifies this really well, why we need something like this, and that's actually the Sahan research project. So I'm going to hand it over to him to talk more about it.
Thanks, Ahmed. So I'm going to give the perspective of the user of the CoDesign lab and tell you how my research benefits from it. So before that, let me start off with a real example of the type of research enabled by this. This is what the Host-FPGA communication looks like for an FPGA attached to a server. The host is running some custom driver to support the PCI communication, which is specific to this FPGA device because the file and the vendor-provided IP core differs from one vendor to another and even from one device family to another. So there's a lot of device-specific data that needs to be captured by this driver. Unfortunately, there's there's not a lot of support, there's not a lot of upstream support in maintaining these drivers. However, if we can use standard internal drivers like VirtiO, we can remove a lot of this overhead of maintaining these drivers. So what we did is implementing a VirtiO compliant interface on the FPGA itself, so that we can use unmodified VirtiO drivers to communicate with the FPGA. Because the VirtiO driver does not differentiate between a physical device and an emulated device, this opens up a lot of new use models, and you can see that it's very handy to have this deployed in a large infrastructure, because you don't have to maintain a whole lot of drivers for these different devices. So this is just my FPGA showing up as a VirtiO console device. This is the PCI devices. But to get there, so doing this research, it has its own set of challenges which make it difficult to use shared infrastructure to do this research. So, for instance, in this particular research, implementing a VirtiO compliant interface on the FPGA means configuring the PCI controller on the FPGA in a very particular way, which is not something you can do easily on a cloud FPGA, because a cloud FPGA usually runs with the FPGA shell, and the user does not usually get to play around with that shell on PCI controller. So essentially, you need bare metal access to the FPGA. Let's say we got that. Because you are configuring the PCI controller and you configure it incorrectly, that does not simply disrupt the host FPGA communication, it can crash the host server as well. So now you can't do this research on a shared server. So you have to have a whole node of HSP also. Let's say we got that as well. When this host machine crashes, sometimes the only way to recover from that is to fully power cycle. So now you need access to whatever the remote power cycle mechanism of that server. So you can see how this increasingly gets more annoying for systems admin, me asking for all these lower level permissions. And this is just for this project. We do not know what level of low level of access we need for the next project. So that's why it's very beneficial to have this on-premise infrastructure to carry out this research until it gets to a point where it's stable enough to transition into this larger infrastructure. So the next obvious question is, why don't you just buy your own machine to do this research? So the problem there is there's multiple research efforts going on at the same time. Not all of those are ready to be integrated together at the same time. So if each of the components will develop on different hardware software stacks, there's going to be a lot of overhead when we are trying to integrate these together again. So code has helped us prevent these research efforts from becoming these one-off implementations which are not compatible with a real-world system, but gives us this incubation step where we can bring our projects to a certain level so that we can safely transition them to wider cloud infrastructure for the next steps. Thank you.